Welcome to this lecture on Six Sigma capability. Our learning objectives today are to explain what Six Sigma capability means, to understand why 3.4 parts per million defective are allowed for a Six Sigma capable process, to relate ppm and yield to Sigma capability, and to use Sigma capability to denote process performance. Now, we learned previously that when a random variable is normally distributed, we have two parameters, the mean and the standard deviation. The function that describes the normal distribution can be integrated then to find the probability that our random variable occurs between 2 points, and we can simplify that by using our standard normal variable, which is a variable normally distributed with mean 0 and standard deviation 1. This is denoted then by the little z. And we can look up those values to find probabilities under our curve in the standard normal tables. Now, if we do this and we look at the probability that our random variable will occur between 1 plus or minus 1 sigma from the mean, we can see that the probability of occurrence is 68.26%, or z equals 1, for z equals 1. Within plus or minus 2 sigmas, we have a 95.44% probability of occurrence for z equals 2. And then for z equals 3, the probability that our random variable will occur between plus or minus 3 sigma from the mean is going to be 99.73%. Again, it's important to understand that the standard deviation is a measure of the variability, and as our production variability increases, the standard deviation of the distribution function increases, and this means that the distribution function spreads out. Now, in the previous lectures, we have studied the concept of process capability. We will now discuss another way of measuring process capabilities in number of sigmas, which is a standard in the Six Sigma methodology. But first, let's review process capability. We learned two matrices, CP and CPK, used to identify the capabilities of process in their ability to meet customer specifications. The CP index compares the natural variability in the process compared to the variability allowed in the specification. For the natural variability in the process, we define this as plus or minus 3 sigma, or in total 6 sigma. And the variability allowed in the spec is going to be then the upper spec limit minus the lower spec limit. Now, for an example, if we have a process where the CP is equal to 1, this means that the variability allowed by the spec, so USL minus LSL, is going to have to be exactly equal to 6 sigma. So you can see here then that means that the upper and lower spec limit are exactly matching the plus or minus 3 sigma point. And this means, as we learned before, that 99.73%, we have a 99.73% probability that our random variable will lie between those two specification limits. Here we show the standard normal again, but this time up until plus or minus 6 sigma. Motorola made a strategic decision in 1986 that they would improve every one of their processes, whether for products or service, to have 6 sigma capability. According to their definition, a process is said to have 6 sigma capability if the defects produced in the process are less than 3.4 defects per million opportunities. This definition for process capability or process quality provides then a common yardstick, whether quality is checked by measuring the characteristics of a product, or, for example, counting the number of blemishes on a surface, or counting the number of mistakes made in a delivery, any type of quality measurement can be then gauged against this level of defects. Now, what we would like to do here is to use our standard normal table again and look up the percentage of the probability that our random variable occurs between plus or minus 6 sigma. And what you see is that you have 99.9999998% probability that our normal variable will occur between plus or minus 6 sigma. And what this means is that if the process is normally distributed, and the specifications the process is expected to meet are located at plus or minus 6 sigma distance from the center of the process, then we have only 2 of 10 to the 9th, or 2 parts per billion units in such a population, or sorry, 2 parts per billion or 0.002 parts per million units would actually fall outside of the specification. However, most processes do not have their mean exactly at the center of the specification because the process tends to drift off center. Therefore, Motorola provides for this fact that processes could be off as far as 1.5 sigma from the specification center or the target. And so I'm going to draw this. So here we have the specification center, the target. And here we have 1.5 sigma. We've allowed our process, even though our process has 12 sigma between the specification limits, we've allowed it to drift. I'm not going to draw this as accurately as I would like, I think, here. But we've allowed it to drift off center. We haven't increased the variability here, but we've allowed we said our process can still be tightly distributed, but it might drift off center. We'll have to do something to move it back. And this, in case you didn't already notice, is where this 3.4 parts per million, this definition of 6 sigma capability comes. Because if the process is off center, if we have our upper spec limit and our lower spec limit so defined, then what we find is virtually nothing out of spec on the lower side, but we end up having 3.4 parts per million out of spec in the process, meaning that we have 99.99966% of our parts or process or product within the specification, and just 3.4 parts per million out of specification. And this is where you see these tabulated for easy reference. The percentage yield and parts per million can be computed, as we learned earlier, by finding the probabilities under the normal curve inside and outside the specifications respectively. Given that the process center is 1.5 sigma away, it's the worst case from their specification center. Now, just a note, if you remember from the earlier lectures, here we are equating DPO and PPM. We're assuming that every unit has one opportunity for a defect, and every defect creates a defective. And here what we can see then for a 3 sigma process, if we perform the calculation, which again you don't have to do because this is tabulated for you, for a plus or minus 3 sigma process allowing for the 1.5 sigma shift, we end up with 93.32% of our product within specification. So for a 3 sigma process, 93.32% within specification, which corresponds to 66,800 or 66,800 parts per million. And then likewise for a Six Sigma process, we have again 99.99966% within specification, 3.4 parts per million defective. So here we show the chart one more time. Some common sigma levels that maybe you could commit to memory. 4 sigma level, 6,200. We've actually seen that in the early examples. We'll come back to that. This can be seen pictorially also here. And actually, if you're from my class at TUM, this is a question on the final. The key takeaway is that the variability of the distribution, the spread, which is as measured by the sigma, should be small compared to the specification limits. So what we have here, let's start with the 3 sigma capability. You see that basically the spread of the process, which we say the allowed spread is plus or minus 3 sigma, so total 6 sigma, falls exactly within the specification limits. So you end up with your CP equal to 1. As you reduce the sigma from your 3 sigma level, you end up then having, you end up having 12 of the reduced of the improved sigma between the upper and lower spec limits. And so what you can see is that your curve is becoming more narrow and more tall. And it fits much more easily between those 2 specification limits. Now, do you remember our automobile example, our car example? If we had 10,000 process steps, each with 3.4 times 10 to the minus 4th % fraction defective. What is our final process yield? That 3.4 parts per million corresponds to 99.99966% good parts for every part or process, which for 10,000 process steps gave us 97% good parts, 97 out of 100 good cars. So again, now we can see that if you have a 6 sigma process for each part or each process in a complicated process, then you can achieve a good overall process yield. And finally, a last question for you all. What is the process capability of our 6 sigma process? Now again, we said here, this is our 3 sigma process. Not a great picture of it though. You have plus or minus 3 sigma on either side, total of 6 sigma between the upper and lower spec limits. For the 3 sigma process, CP equals USL minus LSL over 6 sigma equals 6 sigma over 6 sigma equals 1. What is the process capability for a 6 sigma process? Here we show the 6 sigma process, and we can show that the sigma, I'm going to call it sigma for the 6 sigma process. Here, we're going to have plus or minus 12 sigma for the 6 sigma process within our upper and lower spec limits. And so this means for a 6 sigma process, CP equals USL minus LSL over 6 sigma is 12 sigma over 6 sigma equals 2.